Here's a practice problem for you to try. Please pause the video and see if you can find the equilibrium concentrations. We're going to start by organizing our information in a nice table. So our reaction is I2 yields 2I. We're going to look at the concentrations of I2 and iodine. So it tells us in the problem that we have 1 mole of I2 placed into a 2-liter flask. So 1 mole divided by 2 liters gives us a molarity of 0.5, 1 divided by 2. Because we're with just starting materials, the I is going to be a concentration of 0. If we think about our quotient, Q, we only have the initial concentration of the reactants. There are 0 concentration of the products, and so our Q is going to be 0, meaning our reaction is going to go in the forward direction. Our change is going to decrease the I2 concentration and increase the I concentration. We have a coefficient of 2, so it's going to increase by 2 times the value of x. At equilibrium, we're going to add these 2 columns to find our equilibrium concentration, 0.5 minus x and 2x. Now we can use our equilibrium constant expression and plug in our values. So our equilibrium constant is given in the problem, and it is small, meaning that the reactants are going to be favored. Our initial concentration for the I2 is pretty large, which means that we can make the assumption that the minus x part of the problem is small. So we can try the problem by canceling the x, by simplifying the equation to make the math simpler. So by canceling the x, the problem becomes we're going to move that 0.5 to the other side. When I square the 2, it becomes 4x squared. So now, as we solve the problem, we're going to multiply the 3.76 times 10 to the minus 5th, gives us 1.88, times 10 to the minus 5th equals 4x squared. We're going to divide both sides by 4. And then to get rid of the square, we're going to take the square root of each side. By canceling that x in the denominator, by assuming that it is going to be small compared to the 0.5, it has greatly simplified our math, making it so that we do not require the quadratic equation. And so x is going to be equal to 2.17 times 10 to the minus 3rd. Now we do want to check to make sure that that approximation was valid. So we're going to compare this value back to our original concentration, multiply by 100. And we see that that value is 0.434%, which is less, significantly less than 5%, meaning that our approximation is valid. We can definitely assume that X is small compared to the original concentration. If we do solve this without the approximation using the quadratic equation, we find that X is actually 2.16. And again, this wasn't part of the problem, but just to show you that using the quadratic equation and canceling X, we get values that are very similar. Okay, now let's figure out what our original, or what our concentrations are going to be. So if our X is equal to 2.17, we're going to substitute it back in to our equilibrium concentrations. So for our I2, it's going to be 0.500 minus our X. And we find that that concentration is 0.498 molar. And for our I2, or sorry, I, we get a concentration of 4.34 times 10 to the minus third molar. Okay. If we double check our answer, we can substitute it into the K, the equilibrium constant expression. Plug in our values. Just to make sure that we come up with an answer that's close to our equilibrium constant. And we get 3.78 times 10 to the negative fifth for our equilibrium constant, and that is very close to what we started with, meaning that we have found the correct answer. Here's another practice for you to try. See if you can determine the equilibrium concentrations of dinitrogen tetroxide and nitrogen dioxide. Pause the video to determine your answer. So we are going to set up an ice table again. We're going to be looking at the reaction of N2O4 gives us 2NO2. And so we're looking at the concentrations of each. We're starting with an initial concentration of 0.0125 molar. So that's our initial concentration. The NO2 we have no information about it, so we're going to assume that it is 0, that we're starting with just reactants. This means that our Q is going to be equal to 0. Our reaction is going to proceed in the forward direction. Our change is going to be minus X for the reactants. And we have a coefficient of 2, so it's going to be 2X, making 2X for the products. To find at equilibrium, we add the column together. And now we're going to look at our equilibrium constant expression. You can plug in our equilibrium constant. Oops, I forgot a 0. Okay. We're going to make the assumption that x is small. We'll double check to make sure that that is right, but we can rearrange our equation. Okay, we can solve for x. So by multiplying those two values together, we get 1.34 times 10 to the minus 7 equals 4x squared. We can divide both sides by 4 to get rid of the 4's and take the square root. We find that x equals 1.83 times 10 to the minus 4th. Now, if we check to make sure that our approximation is valid, 1.83 times 10 to the minus 4th divided by our original concentration, 0.0125 times 100%, we get 1.46, which is less than 5%. So this is an valid approximation. We can assume that x is small. Now we want to plug that back in and find the values of N2O4 and our nitrogen dioxide. So take our original concentration minus the x value. And we see that our concentration N2O4 0.0123 molar, and for NO2 it's 2x, or 2 times 1.83 times 10 to the minus 4, which equals 3.66 times 10 to the minus 4 molar. So those are our concentrations. Now just to double check, we're going to put it into the equilibrium constant expression, make sure that we come up with something close to what we started with. So 3.66 times 10 to the negative 4th squared divided by 0.0123. We end up with 1.07 times 10 to the minus 5th, which is exactly what our equilibrium constant was, so we know that we've done this problem correctly.